implicit differentiation. All right, now, in the lab that we looked at yesterday, or that you looked at on Tuesday, one of the list of commands that you looked at in part 1 was a command called contour plot. And that contour plot function, or that command that you used in there, you could type in an equation that involved x's and y's and not necessarily a function, just a whole bunch of x's and y's all mixed together. And this contour plot would give you a picture. In particular, the picture that you saw looked something like, I don't know, I kind of felt like it looked like a little buggy on top of a hill or something like that. So hopefully your curve looks something like that. Okay? And so these types of curves are the types of curves that we're going to study in the section 2.6. Okay? So not every curve that we can draw can be defined explicitly as y is equal to some function of x. For example, this particular little picture with the buggy up here definitely does not pass the vertical line test. Even, no matter where I draw this in the xy plane, this guy is not passing the vertical line test. Okay, so not all curves are described explicitly by y is equal to f of x, meaning that we can't write y is equal to stuff on the right-hand side that only involves x's and numbers and pluses and minuses and things like that. Okay, so not everything can be done like that. Now, for example, besides that buggy picture over there, an easier one is x squared plus y squared equals 25. So if this equation jumps out at you from a dark alley, x squared plus y squared equals 25, what would you immediately think of?
Circle.
Yeah, you're going to think of a circle. It's going to be a circle of radius 5, and it's centered at the origin. Okay, so here's our circle with radius equal to 5, centered at the origin. All right, now my next question for you is, I'm going to give you a point, and I'd like you to figure out whether that point lies on the circle or not. And the point that I'm interested in is the point 3, comma, negative 4. So the question is 3, comma, negative 4 on the circle x squared plus y squared equals 25? All right, I'd like you to think about that for a second. And then I'd like you to talk with your neighbor about whether 3, comma, negative 4 lies in the circle. And whether your answer is yes or no, how do you know?
Yes.
Okay, why do you say yes? Okay, so we've got one answer of yes, and can you say why a little bit louder?
Yeah. You plug in the
numbers in the equation, so it's 25.
Okay, so if we double check, if we plug in the x equals 3, y equals -4, we've got 3 squared plus -4 squared, which is 9 plus 16, and that's definitely 25. So yes, this point 3 comma -4 lies on this circle. All right, so in particular, 5, 4, 3, 2, 1. So in particular, we've got the point 3 comma 4, which is somewhere right around down here. All right, so yes, our point does lie on the circle, and here it is. Now, this is a calculus class, so what we're really interested in this class is talking about slope, and related to slope is tangent lines. And so I might want to draw a tangent line to this circle, which is, by the way, where this word tangent comes from. Initially, the word tangent line is a line that just touches a circle exactly once, and then we sort of take that idea and use it for curves in general. But here is our tangent line. And so we'd like to find the equation of the tangent line to the circle at the point 3 comma -4. All right, so we want an equation of a tangent line. The equation of any line, we need two pieces of information. We need a point, and we need a slope. So our point is easy. That was given to us. That's the point 3, -4. And we double check to make sure that that was on the circle. And it is because it satisfies our equation for our circle. And so the point is 3, -4. And our slope, well, to figure out the slope of a tangent line, we'd want a derivative. Now, with this circle here, I don't actually have an equation that says y is equal to stuff in terms of x. Okay? And in fact, the circle is not a function itself. Okay? So this becomes a problem. But it's not too terrible of a problem to solve. I mean, I can take this equation here, and I can solve this equation for y, and so I think maybe I'll do that. So to find our slope, we want to find y prime. We want to find a derivative, y prime or dy dx. So also known as dy over dx. So this first method that we're going to look at, method number 1, is that we're going to take our equation x squared plus y squared equals 1, and we're going to solve for y. So when I solve for y, I get y squared is equal to, oops, that's not a 1, that's a 25. Y squared is equal to 25 minus x squared. And now when I take my square root of both sides, I get y is equal to plus or minus the square root of 25 minus x squared. Now, that's still not a function, because a function we give one x input and it gives one y output, but with the plus or minus that really gives two values. So this is really two parts to this circle. The positive part is the top half of the circle, and the negative part is the bottom half of the circle. And in our case, because our point is down here on the bottom half of the circle, we are interested in the equation which defines the bottom half of the circle. So we're going to choose the negative because our point is on the negative y side of the circle. So what that tells us is that the bottom half of of our circle is given by y is equal to negative square root of 25 minus x squared. Okay, are there any questions about that equation? I mean, this is great. We've just taken what was a curve, but not a function of x anyway, and we eliminated the top half, and we're only looking at the bottom half of the circle now. And so if I want to find the slope of this tangent line, the slope when x is equal to 3 and y is equal to negative 4, well, I need to differentiate the bottom half of our circle. All right, so if I want to take a derivative, the very first thing I want to do is to rewrite any sort of square roots I have. So we have negative 25 minus x squared raised to the 1/2. And so now, when I want to take this derivative, what rule am I going to have to use? The chain rule. We've got an inside function and then an outside function. Now that negative, that's a negative 1 multiplied by everything. So I'm just going to carry that along all the way through all of my calculations. So we've got y is equal to negative, okay? Our inside is 25 minus x squared. So we have derivative of the outside, 1/2, keeping the inside the same, 25 minus x squared, raised to the negative 1/2. So derivative of the outside, keeping the inside the same, times the derivative of the inside. Now when I take the derivative of the inside, derivative of 25 is 0. And then I have derivative of negative x squared is negative 2x. And this is, yes, thank you, that is our y prime. All right, so that's a fine final answer. Since we're going to be analyzing this, I'm going to simplify and clean up a little bit. I've got a 2 in the denominator as well as the numerator, so those will cancel. The negatives will cancel. And so I'm left with y prime is equal to an x in the numerator. And this negative 1/2 power, well, the negative throws it into the denominator, and the 1/2 makes this a square root. So we have x over square root of 25 minus x squared.
If that's as far as we were going to go, though, the first y prime answer would be fine.
That's correct.
Okay.
If I was just asking you to take a derivative, first row here would be fine. All right, other questions about finding y prime? Done?
And just future reference, would you rather us not have a square root in the bottom?
I don't care if there's a square root in the bottom. In terms of final answers, if you have a final number answer, it's nice to rationalize the denominator, but in terms of our functions like this, square root in the denominator is fine.
Can we make an assumption that if we go to a point negative 3, 4, we would have the same slope?
Negative 3, positive 4?
Yeah.
That would be a pretty good, that would be a good assumption, and you can verify that by, choosing the positive version, and then eventually plugging in x equals negative 3 instead. Okay, so here we've got our y prime, and we'd like to know the slope when x is equal to 3. When x is equal to 3, our y prime value looks like 3 over the square root of 25 minus x squared, so minus 3 squared. And so we've got y prime is equal to 3 over square root of 16, which is 4. All right, so our slope is 3/4. That's a positive number, so that's good because our line is definitely going uphill here. Okay. And so now we've got our slope. We've got our point, and we can write our equation of our tangent line.
I have a question. If that's a tangent line, couldn't we just put with those 2 points? Like how finding the tangent of that point?
So on a circle, because this is a circle and not some other funny shape,
Okay.
the tangent line is always perpendicular to the radius.
Okay.
And so this radius that I've drawn here, well, how do I get it? I went over 3 and down 4. So the slope of this radius is -4 over 3.
Okay.
And so when I do that, then the slope of the line perpendicular is the reciprocal of this number.
So we don't have to go through all that.
So for a specific circle, we wouldn't have to go through this.
Okay.
For the buggy, we're going to have some other work to do.
Okay.
Okay. So you're right. The geometry of a circle is always going to give us a ratio of these two numbers. Good observation. All right. So the equation of our line, we've got the point 3, -4. We've got a slope of 3/4. And so I can use my point slope form. Y minus y1 is equal to slope times x minus x1. So we've got y plus 4 is equal to 3/4 times x minus 3. So we've got 3/4 x minus 9/4, and we've got y plus 4 on the left side. And if I want to write this in y equals mx plus b form, then I better subtract 4 from both sides. So I've got y is equal to 3/4 x minus 9/4 minus 4. And so that 4 I need to rewrite as 16/4. So y is equal to 3/4 x minus 9/4 minus 16/4. And so our final answer is y is equal to 3/4 x minus 25 over 4. And so this is the equation of this red tangent line right here. All right. Are there any questions about coming up with this tangent line? All right. So really, we've just talked about 2 methods of finding the slope of this curve that's part of a curve that's not a function of x. Number 1 is we can solve for y, and then take the derivative of the half that we're interested in, and then use that derivative, plug in the x value, and then come up with our slope. Option 2, Will's idea is, well, we've got the geometry of a particular circle. So in the case of a circle, well, this ratio, or the slope of this line, is going to be related to the ratio of the x and y values, and then it's going to be the negative reciprocal of the slope of the radius that comes out to that point. Okay, so that will always work on a circle. It won't always work for every other type of curve. Okay. So here lies in the problem. That buggy curve that you saw in the Mathematica code, as well as many, many other curves, it's really hard to solve those equations for y. And so after our 10-minute break, then when you come back, I'm going to talk about a third method of figuring out the slope at this point 3, 4. And it'll be a method that will work for all kinds of crazy curves beyond just a circle. Okay, so please take your 10-minute break, and when you come back, we'll talk about method